All right, well, welcome everybody. It is my great pleasure today to introduce Ismael Bernete, who's joining us today from Oxford. And so Ismael got his bachelor's degree at the Universidad de Granada, one of my favorite cities in the world. And then from then he did his master's at the Universidad de La Laguna, where he worked, as a young person with a very challenging OSIRIS observations. And from there he got his PhD at the Instituto de Astrofísica de Canarias. And after that, he moved to Durham, where he was a visiting fellow. And then he did a postdoc at the Instituto de Física de Cantabria. So very long list of things, even though he's so young. But now he is a postdoc at Oxford. And Ismael specializes on the broad subject that I guess all of us, galaxy evolution, and in particular with the interaction with AGN and feedback processes. He has done a lot of really excellent work with exploiting very high resolution observations and studying the torus, and he has done a lot of work with PAHs, which he will talk to us today about. And I'm super excited because they look amazing. So Ismael has been also a PI for ALMA observations and GTC and a number of other things. But also he is part of, if I'm correct, 3 different JWST programs. So today he's going to share with us some of his results from very, very, very recent observations with JWST. It was very impressive how he got this paper out in August, just very soon after getting the observations. So I'm very excited to introduce Ismael, and thank you for being with us.
Okay, thank you so much. So thank you for inviting me to give this talk, and today I'm going to present my recent work about high angular resolution PAH emission in Seyfert galaxies by using James Webb data. So I'm going to since this audience is people that know AGNs, I'm going to go quite quickly in this kind of a slide for introduction. So we know that AGNs are not longer considered peculiar objects in the universe, but they are now considered as a short but a recurrent phase in the overall life of a galaxy. We also know that there is a strong correlation between the properties of the supermassive black hole and the properties of the host that has been interpreted as a sign of coevolution between the two. We know that this AGN feedback is important in order to explain the formation of the galaxies, and the evolution of the galaxy. According to simulation of galaxy formation, we overestimate the massive galaxies without the AGN feedback. So we need to introduce this AGN feedback in the simulation in order to be able to reproduce the observational data. This AGN feedback is multiphase and multi-scale. In multi-scale, I mean, we can find this AGN feedback very close to the innermost region, close to the central mechanism of these AGNs. We can see also the effect of this AGN feedback at the galaxy scale, and even in strong AGNs, we can see these outflows that are beyond the galaxy disk. In the case of the multi-phase outflows, we know that we can see them in ionized gas, molecular gas, or even in dusty regime. So this AGN feedback can be negative, as we said before, but can be also be positive. I mean, this outflow can compress the gas and produce star formation activity. So this will be a positive way of this AGN feedback. However, to investigate the connection between the AGN and the host galaxy is very difficult because of the very different spatial and temporal scales. So one of the best ways to address this issue is to investigate the innermost region of these AGNs. So this scheme shows the internal structure of an AGN, and according to the AGN unified model, what we have in the innermost region is a optically thick dusty torus that is located between the broad light region and the narrow light region of these AGNs. So depending on the orientation of this torus with respect to the observer, we are going to have a type 1 or type 2 AGNs. We know now that this scenario is much more complicated, that the torus, for example, has a clumpy distribution, and this complicated things with the orientation of the torus. We also know that this torus is very small, and we know that we have other contributors in the mid-infrared that can make obscuration at this scale, like, for example, the polar dust. All this dust is going to absorb a significant part of the intrinsic radiation of the AGN, and then it's going to remit it in the mid-infrared. So because of that, we are very interested in investigating the mid-infrared continua of these kind of sources. Not only because of that, because the mid-infrared waveband is also an excellent regime to investigate that, because we have a lot of different features that we can use. No, for example, finite structure lines that you can have in the low and the high ionization potential, H2 rotational lines that is going to trace the warm molecular gas in these sources, and for example, polycyclic aromatic hydrocarbons or silicate features between others. No? But what are these polycyclic aromatic hydrocarbons? So these polycyclic aromatic hydrocarbons, or PAH in short, are carbon-based molecules that result from the union of several of these basic unit that is the benzene, and with that you can form different sizes of these PAH molecules. They are very well known on Earth, so indeed these molecules are considered to be crucial for the life building blocks, and indeed they are super important for us in our everyday basis, no? Because they are part of the coffee that we need in the morning. But why we are interested in these PAH molecules in astronomy? So these PAH molecules absorb UV photons from the star and then produce very strong different bands in the mid-infrared. This is an histogram showing how is the contribution to the total infrared luminosity of these different PAH bands that we have in the mid-infrared in comparison with other emission lines that are very well known, no? Like H-alpha or carbon-2. You can see that they are extremely bright. And because of that, we are interested on these bands that allow us to observe galaxies that are very distant or very faint. So these molecules also absorb UV photons from the star. We can use, in principle, these bands to trace the star formation activity. No? This has been done for many years now. But this PAH molecule has more applications. For example, these PAH molecules are not only tracing star formation activity, but are also good interstellar medium barometers. So in these two spectra, we show the different PAH bands for these different sources, a planetary nebula and a PDR in the Orion bar. In red are the different PAH bands, and you can see how different they are. No, the relative strength of these PAH features are different in these two sources. Indeed, if one make ratio of these fluxes, one can trace the physical condition of these different sources. No? I'm going to make now like a small break in the talk to talk about another application that this PAH molecule has. So this PAH molecule has been also shown that are very efficient to find obscure nuclei. In a recent work, we were trying to find these compact obscure nuclei, or CONS, that has a extremely high hydrogen column density. They cannot be detected in X-rays, or they cannot be detected using infrared colors, as we did for quantum-seq sources. No? These sources are only detectable by using ACMB emission line, that is a line that we can only detect in the submillimeter by using ALMA or the submillimeter telescope. No? But even with this ALMA telescope, you need to spend a lot of time because this line is very, very faint. No? So this is not really effective for high redshift galaxies. No? To try to solve this, we try to find a way of finding these cones using this PAH emission. No? You can see here the typical spectra of the disk of a galaxy that is PAH dominated, and the typical spectra of a nuclear region of a cone. No? You can see how different they are. No? By taking all together, what we see is that the nuclear region is producing a really strong effect in the equivalent width of the different PAH features. No? By working with these different PAH features and making ratios of the equivalent width, we are able to isolate these cones in a small region of this diagram. So I'm not going to give many details on this, but if you are interested, please check this QR code. So coming back to the other application that we have for the PAH molecules, that is to better understand the physical condition of the sources, we started this project. So this project used density functional theory in order to solve the Schrödinger equation of these molecular systems. With this process, we can produce the mid-infrared theoretical spectra of these PAH molecules. I'm not going to go very deep in all the details of this work, because all of this can be found in Rigo Polo 2021, no? Where we have all the process of producing this mid-infrared spectra of the theoretical PAH molecules. By using this approach, what we have done in our group is to investigate the different properties of the PAH. In particular, so with this idea, what we had is to investigate how the properties of these PAH molecules are, and how this can help us to understand the physical condition in these sources. To do that, we use this approach that uses the density functional theory to solve the Schrödinger equation of these molecular systems. With that, we can produce the mid-infrared spectra of these PAH molecules, and with that, predict the different ratios and relative strengths of the PAH. So I'm not going to give many details on that, because all of this is in Rigo Polo 2021. So in our project, what we try is to understand how the PAH spectra are changing with the properties of these molecules. No? In particular, we have been focusing in the size, charge, and hardness of the radiation field. No? All of this has been published in this paper if you are interested in more details. In particular, in Rigo Polo 2021, where we present this theoretical spectra, we also explore how the different ratios give us properties of the PAH. No? In particular, we found that the band between the 6.2 and 7.7, this ratio is a good tracer of the molecular size. The 11.3 over 7.7 or 11.3 over 6.2 is a good tracer of the ionization fraction. So this is in agreement with previous work using different approaches. So once we have this theoretical spectra, what we would like to do is to produce some grids and compare with observations. So in this first work, what we did is we compared the observational ratios with those of the theoretical spectra for star-forming galaxies and Seyfert galaxies. In this first work, we used the species data because it was the only data set that we had at hand at the moment, no? Waiting for James Webb. So in this work, we use this telescope species that is 0.6 meter diameter. It's not very big, but it's a telescope that has produced a lot of data and has produced a lot of science. No? This telescope is working in the mid-infrared and allow us to investigate the PAH emission of these galaxies. In this work, we use the Sweetbat AGN catalog. That is one of the most complete catalog to date. and we use a distant limit in order to ensure some resolution element, no? Less than 1 kiloparsec. It's not great, but at least this allows us to disentangle the central region of the AGN and the extended region of these AGNs. So using this sample of 50 Seyfert galaxies, we have a sample that is representative of the entire group, no? In terms of hydrogen column density and X-ray luminosity. So in this work, what we would like to do is to compare how are the PAH emission of the AGN compared with a control sample of star-forming galaxies. In this first part, what we did is we compared the 6.2 over 7.7 ratio, that is, as we said before, a good tracer of the molecular size of star-forming galaxies and AGNs. What we found is that for AGN-dominated system here in the right panel, we found that these galaxies has slightly smaller values of the 6.2 over 7.7, no? Telling us that these galaxies should have in the central region larger fraction of larger molecules, no? In comparison with the star-forming galaxy that has larger fraction of small PAH molecules. If we move now to ionization fraction, we should use this ratio 11.3 over 6.2, and we compare star-forming galaxies again in the left and AGNs in the right. We can see that AGN-dominated has larger values of this 11.3 over 6.2, telling us that this central region of this AGN has larger fraction of neutral molecules. Now we can compare with our grids, and what we see is exactly the same, no? We see that the star-forming galaxies are allocated in a particular region of this grid, well concentrated. However, the AGNs are more spread, and in particular, AGN-dominated system has larger fraction of neutral and larger fraction of large molecules. Since we can produce an extraction in the extended emission, we can compare this central region with the extended emission. And what we found is the following, no? In this right panel, we can see the comparison between the central region and the extended region of each of these AGNs. I call them central because it's not nuclear at all, no? It's 4 arcseconds. So this will be, like we said before, around 1 kiloparsec, no? So it is not nuclear. So we can see that the extended emission that is represented here by stars are very well concentrated in a region of the PAH diagram. Indeed, they are very close to the average value that we found for a star-forming galaxy, this gray shadow region that is here, no? However, the central region of the AGNs has more spread in the PAH diagram, and also they tend to have larger fraction of neutral molecule and larger fraction of larger sizes, no? However, these results are not completely clear because of the angular resolution, no? We are very limited here by the low angular resolution by species, no? So we really need a higher angular resolution to go to the nuclear regions. So the main conclusion of this work was that the AGN that has a composite system of AGN and star bus, or they are really weak, they are very similar to star-forming galaxies in terms of the PAH properties, no? Also, the extended emission of these AGNs show PAH properties that are very similar to the one that we found in star-forming galaxies. However, only these central regions show PAH properties that are slightly different, no? So they show a ratio that can be explained with larger fraction of these neutral and large molecules. Therefore, this show tentative evidence that the AGN-dominated system can produce some changes in the PAH population, no? But as we said before, this is very limited by the low angular resolution that we have with the species, no? We really need high angular resolution data to be able to be close to the AGN, no? Where most of the action is taking place, no? For that, JWST data is going to be really good, no? And we are going to see in the next part of the talk. So in this second work, we are going to investigate this PAH emission in Seyfert galaxies using high angular resolution data provided by James Webb, no? In this part, we are going to use the James Webb Space Telescope. Everyone knows this telescope now, but this is the most powerful and complex telescope that has been ever deployed in space. No, this is a really complex observatory that has a very different instrumentation. No? In the near infrared, for example, we have NIRPE that is working in spectroscopy. We have also in the near infrared NIRCam that is making images. And in the mid infrared, we have, for example, MIRI, no? That has the two different modes, working in images and working in spectroscopy. It's a really a good improvement to use James Webb Space Telescope, because this telescope is around 10 times bigger than Spitzer. No, this will provide an angular resolution that is 10 times bigger, no, and much more sensitive. So this telescope is working well. It's observing already science. All the commissioning has been done, and the first data was released by July 2022. No? From this day, we were working on this project. What we did is we went to the James Webb archive, and we picked up all the Seyfert galaxies that were public. In particular, we took this set of 3 Seyfert galaxies. The 3 Seyfert galaxies that we are using here are NGC 6552, which is a Type 2 AGN, and is part of the MIRI commissioning observations. We are also using 7319, which is also a Type 2 AGN and is part of the early release observations. And we are using also 7469, which is part of the early release science program and is a Type 1 AGN. This galaxy that you can see here in the left panel, this is a NIRCam image of James Webb. You can see that this galaxy is has a quite beautiful extended emission, and this galaxy is quite interesting because also has a star-forming ring that shows several mid-infrared clamps, and also have a nuclear starbus. So if we make a zoom in this nuclear region, what we have is this field of view that we can see in the right-hand panel. This is a map that we produce from the MIRI spectroscopy observations in the channel 1, that is the one that shows the smaller field of view. And this field of view already is enough to study the circumnuclear star-forming ring. No? You can see that this field of view is more or less the same angular resolution that we had with the Spitzer, meaning that we are going to improve a lot in our study of this nuclear region. No? We can see all this detail now. No? So this study is going to allow us for the first time to characterize the path properties in the nuclear region of local luminous Seyfert galaxy at sub-second scales, and using the entire mid-infrared range. So for selecting the different regions that we are going to study, first we took all the nuclear region of the different AGNs using 1 arc-second diameter aperture. And for the circumnuclear region, we use mainly the circumnuclear region of 7469. This is because 6552, which is the galaxy that was part of the commissioning, was not designed this observation to make science. This means that they didn't make any dither at all, so there is no dithering in this observation, and this makes quite difficult to use the extended emission of this galaxy. In the case of 7319, this is also a galaxy that has been previously investigated in Pereira Santa Ella 2022, and we know that the extended emission has no PAH emission at all. No? So the best goal that we had is to have a look to the circumnuclear emission of 7469. That is also a really good case for investigating the star-forming activity, because we have all these very bright clamps, no, in the circumnuclear star-forming ring. However, this galaxy has more things going on. So in order to select the region that we are going to investigate in the circumnuclear emission, we make different maps in order to select them. So in the top row of panel, you can see the intensity, velocity, and velocity dispersion maps of the sulfur 4 line. This line is a good tracer of the AGN, and we can see in the velocity and velocity dispersion already that this galaxy has a outflow, nuclear outflow in the east to south direction. No? If we compare this velocity dispersion and velocity map with the velocity dispersion and velocity map of the H2 line, this H2 line is tracing the warm molecular gas and therefore is mainly tracing the rotation of the galaxy. So we can see how different are the two velocity maps, and this is just showing that this galaxy has this nuclear outflow. So in order to select the regions, we need to take into account all this morphology. So using MIRI and using specifically this filter, the 7.7 micron filter, we select the different region that we are interested in this work. So we select regions along the star-forming ring, but also we select regions that are along the projected direction of the outflow. And we also take a couple of more regions in the diffuse extended emission for comparison. So this galaxy has a lot of star-forming activity going on, so we can have a look to the PAH maps just to see how they are tracing the star-forming activity. So for producing these PAH maps, we are using the local continuum in order to produce this map, which is not great, but at least is a good solution to get some idea of this PAH emission. In the 6.2 map, we can see how this feature is tracing quite well the same structure that we have in the argon 2, which is a line that is tracing mainly the star formation activity. No? However, in the nuclear region, we are starting to see some differences. No? Also, we produce a first attempt to investigate these ratios in a map using these different maps from James Webb, tracing the 11.3 and 6.2 PAH bands. No? So what we can see here is that these ratios are indeed quite different already for the circumnuclear ring in comparison with the nuclear region, no? Showing the nuclear region larger values of this PAH ratio. No? That is telling us that the nuclear region has larger fraction of neutral molecules that we found in the central region of AGNs in the previous work. However, to make a proper estimation of these fluxes, we need to proper model the dust continuum, no? And this cannot be done with a local continuum. So in order to do that, it's quite difficult to make this at the moment, spaxel by spaxel, due to the current status of the pipeline. No? So in order to do this, what we have done is to select the different region that we said before. No? This is the main motivation between taking these different regions. So I'm going to show now the spectra that we extracted with James Webb. So in the bottom panel, you can see the three different nuclei. So the first thing that is quite interesting is that indeed all the nuclei show the PAH emission, in particular the 11.3 is present in the three nuclei, and all the other bands are indeed present in the 75, 65, 52, and 74, 69. However, 7319 has very little contribution of the 7.7, or indeed can have no emission of the 7.7, depending on how you fit this spectra. This can be related with the fact that this galaxy has been in many interactions, so has lost a lot of the gas, and this can be producing this low PAH emission. Just for comparison, I also show here a star-forming clamp. I'm showing just one of them because the spectra of all these clamps are very, very similar. We are going to see in the next slide. To fit all these spectra, we use PAFIT, which is a well-known software to extract the path fluxes in star-forming galaxies and AGN. And in particular, we use our modified version of PAHs that is adapted to work with James Webb data. No? This is produced in our group and has been done by Fergus Donald, which is a PhD student here in Oxford. So once we have the continuum, we can subtract the continuum to the spectra and produce the PAH spectra of the different regions. In the top panel, we have the PAH spectra of the two nuclear regions of the AGNs, for a type 2 in blue and for a type 1 in black. And you can see in the central panel the different star-forming regions that we extract in the circumnuclear emission of 7469. You can see that the star-forming regions show PAH profiles that are very, very similar. And indeed, we can average them and make a PAH template because they are indeed quite similar, all of them. No? This was a little bit surprising for us. Then using this average template, we can compare them with the other aperture that we extracted along the outflow direction. And we see that they are indeed very similar. And the only differences are in the 6.2 and 7.7, no? Telling us that these regions are slightly more neutral than the one that we found in the star-forming regions. In the bottom panel, we have the theoretical PAH spectra, where we can see how powerful is this approach to predict where the peaks are going to be in the observational data. No? So you can see how well explaining are the different peaks, like for example 8.6 or this bit in the 11 microns and so on. No? So another result from this first look to the spectra is that we can indeed clearly resolve some of the PAH bands that were previously blended in complex, like for example the 8.6 one. No? You can see now clearly the wings of the band. However, to investigate the properties of the PAH, the best way to go is to take the fluxes and make ratios as we did before, no? And compare with the theoretical grids. So this is what we did here for the 3 Seyfert galaxies. You can see here the 3 nuclei for the galaxies, and these star symbols correspond to the circumnuclear emission of 7469. So first thing that we saw is that the nuclear regions are distributed in the PAH diagram, and they are not very close, but they are indeed different to the regions that we found in the circumnuclear emission. No? These ratios show larger fraction of the 11.3 over 7.7, telling us that this nuclear region has larger fraction of neutral PAH molecules. However, the star-forming regions are very well concentrated, and indeed these ratios are very similar to the one that we found as in Spectral for the average value of the star-forming galaxies. Here I also show you, just for comparison, the central and extended value of 7469 that we have from Spectral. So you can see that the 2 points are very close, and this is because the angular resolution that we have for 7469 using Spectral is the same that we have for the entire field of view of James Webb data. No? This is meaning that all the star-forming ring is within the aperture, and then makes sense that the ratios that we found are very similar to star-forming galaxies. Now, if we make a sum of these star-forming regions, what we found is that the regions that are allocated in the same direction as the projected direction of the outflow show slightly different values of the 11.3 over 7.7 than the other star-forming regions. This is telling us that these regions along the outflows are slightly more neutral than the other clamps. However, I think that this is not more related with the fact that the outflow is in this direction. It's more related with the fact that these apertures show a low infrared surface brightness. No? This means that they have very little contribution of the star formation, and therefore they have not a large amount of UV photons that can ionize these PAH molecules. So from this plot, the main conclusion will be that the nuclear region of AGNs show larger fraction of these neutral molecules than the case of the star-forming regions. No? To explain this difference, there are different possible scenarios. No? For example, one of them should be that the neutral PAH molecules can be protected by the large amount of hydrogen column density that we have in the central region of AGN. So we know that in the central region of AGN, we are going to have a lot of dust, hydrogen, material. All of these can be protecting this molecule from getting ionized. Another scenario is that the strong or hard photons from the AGN is not significantly contributing to the photoionization of the PAH emission. However, the UV photons from the stars are more efficient by ionizing these PAH molecules. And the third scenario will be that these ionized molecules, which are weaker or are less resilient than the neutral one, can be more easily destroyed in the nuclear region of AGN by these very hard radiation fields. So the main conclusion of this work is that this first data set of data from Webb allow us to investigate for the first time the PAH properties in the nuclear region of local luminous Seyfert galaxies, that although some previous work were predicting that the destruction of the PAH should be occurring in the central region of these luminous AGNs, our work found that PAH molecules can survive in the innermost region of this AGN. In particular, we also found that they show not only one of these bands, but they show like all the bands that we were expecting to have in the mid-infrared. No? We also found that thanks to this very high spectral resolution, we are able to resolve some of these PAH bands that were previously blended in some of the complex, like the case of the 8.6. We found also that all the star-forming regions show very bright PAH emission that was expected, but also they show very similar, practically identical PAH profile. No? That is kind of surprising. All the nuclear region of the AGNs are located in the PAH diagram in different regions, but they are all in larger values of the 11.3 over 7.7 in comparison of the star-forming regions. On the other hand, the star-forming regions are very well concentrated and very close to the average value that we found previously for star-forming galaxies in using the SPICER data. So in the nuclear region of the AGN, we have the PAH emission that is coming mainly from the neutral PAH. However, in the star-forming regions, what we have is emission that is coming mainly from ionized molecule and probably smaller sizes than in the case of the nuclear regions. This can be explained by different reasons, as we said before. One of the main results is also that our study provides evidence that the AGN indeed have an impact in the properties of the PAH molecules on nuclear scale. No? So this means that we need to be careful when we use these PAH molecules as star-forming indicators in the vicinity of the AGNs. So that will be all, but if I have 2 minutes, I would like just to show what is next in our group. So as part of the GATOS collaboration, we have 2 different cycle 1 James Webb proposal accepted. So one of them is going to be focused on characterizing the torus and the polar dust using James Webb MIRI images. And this is going to clarify if this dust is just dust in the narrow light region illuminated by the AGN, or this is part of a dusty outflow. In the other proposal that we have is the main goal is to characterize the multiphase outflow in the innermost region of these Seyfert galaxies by using James Webb data, but in this case using spectroscopy and making mapping around this nuclear region. For that proposal, we have a representative sample of Seyfert galaxies that we also plan to apply to these polycyclic aromatic hydrocarbon studies to have a representative sample of these galaxies. So this will be all. Yes, thank you. If you have any question, I will be happy to take it. I'm sorry about the problem with the connection.
Thank you, Ismael. That's a very mind-bending presentation. I mean, it's very mind-bending results. I'm very puzzled by your results. Very excited to see that. Yeah, so are there any questions from the audience? I guess I'll just say, oh, Shavita, yes.
Very nice talk, Ismael. Thank you so much for sharing all of that. I had two quick questions. One is, apart from the line ratios in the nuclear region and circumnuclear region, what fraction of the luminosity in the PAHs is coming from the nuclear region versus the circumnuclear region? That was the first question.
This is a good question, but it's true that we didn't compare that. No, this is part of the more detailed analysis that we need to do. No, so it's something that we need to check just to see how the AGN can affect this luminosity. No, because there are also studies that say that PAH emission can come from the excitation of the photons from the AGN. No, so this is something that we need to investigate. But as I said, this is not. It's something that we didn't have a look still. So.
Oh, okay. I was curious. And then the other thing is that the three nuclear regions are in very different locations in your ratio diagram. And I wondered, why do you think that is? I mean,
yeah, so this is a good question indeed. So this is because also of the sample that we are using is not a sample that is designed to get a statistical conclusion. No, for example, 7469 is a type 1 AGN, but also has a nuclear starburst. No, this can be contaminating our nuclear PAH ratios. No, in particular, I think that is affecting 6.2 over 7.7. No, I will expect to have this galaxy in this region if we are able to get rid of the starburst. No? However, to compare that, we need another type 1 that has no signs of an starburst in the nuclear region. At the moment, we don't have it. No? So the other one is 7319, which is an upper limit. No? So this galaxy show an upper limit because 7.7 is not clearly detected. No? However, this one show 11.3. No? So for sure, we are sure that they should have larger fraction of neutral molecule, no? Because if you have 11.3, this is, if you have nothing on the 7.7, you are even above this point, no? So the result that is clear is the fraction of the ionization, no? Less clear is the size, but I think that this is in principle related with the fact that this galaxy has a nuclear starburst, no? So yes, what we need is more observations and trying to.
Yeah, I mean, it's hard with such a small sample, but I was curious if somehow the ratios could tell you something about the nucleus. I mean, the accretion properties, the hardness of the radiation field, or something that could.
Yeah. So the main thing is that we need more statistics, no, to try to figure out how this is happening, no, because we also found this with the species data, no. So the nuclear region should normally is more spread than the star forming regions, no.
Thank you.
There's a question in the chat from Torsten. What aperture size did you use to define nuclear in NGC 7469?
Yeah, so this is 1 arcsecond diameter, and then we apply aperture corrections in order to recover the nuclear region. So in principle, we could do something smaller, but we have been working around, and with the aperture correction, the spectral was very similar, even doing something smaller.
Okay, let me maybe explain the background. I was wondering whether you're comparing apples and apples in the sense that you should comparing the same physical size of the nuclear area region. Because I don't know how much variation there's in distance off the top of my head.
Yeah,
But
so
if you're just comparing the same angular size, then you may be contaminated by the surrounding stuff more than any nuclear star cluster or anything.
Yeah, this is a good point. So in this particular case, these three galaxies are very similar in distance, no? So it's not an issue. But it is true that when we expand this sample, we should be careful with that. Yeah.
Richard? Richard, you're muted.
Try that again. Thank you. So these three objects differ a fair bit in their luminosity and masses of the black holes. And so, again, for a fixed aperture, you're looking at different effective ionization parameters or whatever the free parameter is in the model for the photon field hitting the PAHs. Have you looked for any relationships between mass, luminosity, and your ratios?
No, we didn't. So this is part of the plan. So this is something that we expected to do. So at this stage, what we did is just focus on the properties and show the different nuclei, different types. But this is something that we need to have a look for sure. Yeah, good point.
What about in the original Spitzer data?
So the original species spectra is only available. You mean the comparison between James Webb and
No, I mean correlations in the ratio.
Yeah, so for correlation we tried to look something, but we didn't find anything very clear with luminosity or this kind of property. The only thing that we found some trends were when we were comparing with the hardness of the radiation field, no, with neon 3 over neon 2 or colors or this kind of thing. This kind of thing shows some kind of relationship with the PAH ratios, but we didn't find anything very clear with luminosity or so on.
Thank you.
Any other questions? I was a little confused by, so you have three scenarios of why the ratios appear more, why it appears more neutral. And the third one was, no, the second one, the AGN is not significantly contributing to the photoionization. I mean, the whole thing seems counterintuitive to me. I'm sure to you guys too. But so if that is the case, then how do you explain the different ratios? How do you explain that they're so different?
So the main difference is in the you mean nuclear versus circumnuclear, no? So yes, so the main difference will or no?
No, so these are scenarios for explaining the larger fraction of neutral PAH or PAH molecules in the nuclear region, right?
Yeah.
So if the AGN is not significantly contributing, why is it different from the circumnuclear?
Yes, so this can be explaining with the others. So one thing is that one thing that can happen, we need to look this in detail, will be that you have a lot of this hydrogen close to the AGN that is protecting these molecules, no, all of them. However, indeed, scenario 1 and 3 will be kind of connected, no, because you have all this hydrogen that is protecting all the molecules. However, the ionized ones are weaker, are less resilient than neutral ones. So in this hard radiation field, the AGN will destroy first ionized and then neutral. So what you are going to have in close to an AGN is a larger fraction of neutral because of that.
Okay, I think I understand. I was a little confused by that. Okay, thank you so much. Just very quickly before we go, if any student wants to join a student discussion afterward, the link to the Zoom session is on the chat, and Jeffrey, who just turned on his video, will be hosting it. So let's thank Ismael again for a great talk, and see you in a couple of weeks.